So I'd been getting several questions about the homework problems, specifically number 3, and how to tackle these. And I thought I would go through a couple examples, the ones that I've gotten the most questions on, to show you some of the techniques that you're going to be using, not just in this homework, but throughout the rest of this chapter and actually into the next chapter as well. And so the two that I chose in particular are 3A and 3B, or excuse me, 3D. And so in each one of these, they give you a rule for the nth partial sum, and they want you to find a rule for u sub k. Just so there's no confusion here, when they ask you to find u sub k, this is what we did last year when we found the nth term of a series. So instead of using a, they're using u. Instead of using n, they're using k. But essentially, they want you to write a rule that allows you to find the nth term in a particular series. So if you wanted to find the third term or the fifth term or the 100th term. And so I'm going to start with A. And so they provide you with the rule for the nth partial sum. So anytime this occurs, when they give you the rule, just go ahead and find the first few partial sums, and hopefully you'll be able to use those to then find the first few terms in the series, and then hopefully look for a pattern. And so if I find the first partial sum, given the rule 3n squared minus 1, I plug in n equals 1. So 1 squared is 1, times 3 is 3, minus 1 is 2. So the first partial sum, which is just the first term of the series, is 2. Next, we find the second partial sum, which is the sum of the first two terms in the series. And I do 2 squared, which is 4, times 3, which is 12, minus 1, which is 11. And then the third partial sum is 3 squared, which is 9. 9 times 3 is 27, minus 1 is 26. And the fourth partial sum is 4 squared, which is 16. 16 times 3, which is 48, minus 1, which is 47. So using these first four partial sums, I now would like to find the first few terms in the series. So I know the first partial sum is the first term, which is 2. The second partial sum is the sum of the first two terms. So if I know the first term is 2 and the sum of the first two is 11, that tells me that the second term in the series is 9, because 2 plus 9 gives me 11. And so basically, you're just finding the difference between the partial sums, and that will give you the next term in the series. So here, the difference between 11 and 26 is 15. So that tells me that the third term in the series is 15. And then to find the fourth term in the series, I just find the difference between 26 and 47, which gives me 21. So the first four terms in my series are these. And you can continue on, but I think we have enough information from those to figure out what's going on. So this is the first main issue that pops up. What we're looking for is we're looking for a pattern in these first four terms. And so if we look at the first, going from the first term to the second term, it looks like it adds 7. But then from the second term to the third term, it adds 6. And it seems like it continues that pattern, plus 6, plus 6. And just to demonstrate what that would look like, let's go one term deeper here, and let's find the fifth partial sum. So coming back up here, 5 squared is 25, times 3, which is 75, minus 1, which is 74. And so I find the difference between the fourth and fifth partial sums, and that gives me the fifth term, which ends up being 27. And so it looks like our pattern is linear, where it adds 6 each time, except we've got a problem right here where the first term doesn't seem to follow. So for right now, and I'll address this at the end of the problem, I want to ignore this particular problem. And so if we have plus 6, I know I have a linear pattern, which means this is an arithmetic series. And so what I'm allowed to do is, if it's arithmetic, then it will follow a linear pattern. And so using some of the rules from sequences in series, if I want to find the nth term in an arithmetic series, I have a sub n is equal to a sub 1 plus the common difference d times the quantity n minus 1. And so we have a couple things here that we need to find. So first, I do not know what the first term is, but I do know that the common difference here is 6. Again, we're ignoring the 7th for right now, and we'll come back and address that a little later. So we have 6 times the quantity n minus 1. But then right now, I don't know what the first term is. And so your first term, you would think would be the 2, but it's actually not, because if we're following the pattern here of plus 6, I actually have to work backwards and do minus 6, minus 6. And so based on this pattern, if I do 9 minus 6, the first term will actually be 3. And so expanding this a little and simplifying, I get a sub n is equal to 3 plus, and then I go ahead and distribute the 6. I get 6n minus 6, which gives me a rule for the nth term being 6n minus 3. And you can think of this as y equals mx plus b. The slope is 6, which we said was the rate of change. And then where did this negative 3 come from? Well, if you work backwards from the third term to the second term to the first term, and then even though it doesn't exist, imagine that there's a 0 term here. So if I subtract 6 from 9, I get a first term equal to 3. And if I subtract 6 more, I get a 0 term of negative 3. Now again, there is no 0 term, but we kind of use that idea to work backwards to find our y-intercept. So this is actually the answer to part A from problem 3, but we still have this problem floating around, what to do with this plus 7. And so one of the ideas behind sequences and series, when we do these infinite series, is sometimes we have these weird rules that occur early on, but once we get past that early rule, the series tends to follow a nice, neat pattern. And so I really don't care at this point that there is an issue early on, as long as I keep moving out to the fourth term and to the fifth term, does this rule actually hold? And so just to test this, if I were to plug in n equals 5, 6 times 5 is 30, 30 minus 3 is 27, which is what our fifth term was. So it is okay, even though you might feel uncomfortable with it, that it's not working for this first term right here. So what we need to do is just add an additional rule in here. So we are saying that the nth term in the series is 6n minus 3, except that starts at the second term. So what we're going to do is we're going to add a little disclaimer here that this rule only applies when n is greater than or equal to 2. And so that is something we will find next section when we start exploring some of these different series that are not arithmetic and they're not geometric. It has some weird behavior going on early, but as long as that behavior kind of works itself out once you start moving further into the higher values of n, that we're okay with that happening. So again, we'll address that in section 3b. The second example I want to work through is number 3, and this one also brings in kind of a unique concept that might be a little harder to follow, but I think you guys, once you see what happens, you'll know to look for it. And so we're going to do the same thing. In problem 3, we're given the rule for the nth partial sum. So let's do the exact same thing we did before, which is let's just list the first few partial sums. And so the first partial sum in this case is just the natural log of 1, which is equal to 0. And what we're going to find is I actually don't want to simplify this. And you'll see why a little later, why we do that, because it'll make it a little more difficult to identify what our rule is going to be. But for right now, we'll go ahead and leave it as the natural log of 1, which is equal to 0. And then the second partial sum, which is the sum of the first 2 terms in the series, is just going to be the natural log of 2. And the third partial sum will be the natural log of 3, and the fourth partial sum would be the natural log of 4. And so this seems pretty simple, where if you're just finding the first partial sums, if I asked you what the 10th partial sum is, we know that that would just be the natural log of 10. But using what we did in 3a, the whole point of these partial sums is to be able to work backwards to find what the first term, what the second term, basically what all the terms in this series are. And so right here, the first partial sum, in this case, is the first term in the series, which is just the natural log of 1. But now the second partial sum is the natural log of 2. We need to somehow use that to find out what the second term in the series is. And so before I do that, I want to slide this over and this over, is to look at how we actually find the second partial sum. So the second partial sum is the sum of the first 2 terms in the series. And so I already know that the first term in the series is the natural log of 1. So if I plug in the natural log of 1, wrong spot, natural log of 1 for the first term, and then I ask you what is the second term here. Well, if I solve for the second term here, I need to take this natural log of 1 and subtract it over to the other side. So the second term in the series is actually the natural log of 2 minus the natural log of 1. Continuing that pattern, if I ask you what the third term in the series is, well, to get the third term in the series, you basically find the difference between the second partial sum and the third partial sum. So what am I adding to get this? Well, we can't really add something to the natural log of 2 to get the natural log of 3. So what I find is the third term is actually the natural log of 3 minus the natural log of 2. And I'll do it one more time just to show you how we get that, is the third partial sum is equal to the sum of the first 3 terms in that series. And we already established early on that the first term in the series was the natural log of 1 plus the second term in the series, which we said was the natural log of 2 minus the natural log of 1 plus whatever the third term in the series is should give us the third partial sum. And so now I already know that the third partial sum was equal to the natural log of 3. And notice here I have the natural log of 1 minus the natural log of 1. Sorry, there's a minus sign there. It shouldn't be there. And so that leaves me with the natural log of 3 is equal to the natural log of 2 plus whatever the third term in the series is. And now, similar to what we did before, if I want to know what the third term is, I need to subtract the natural log of 2 from both sides. And so in this case, the third term in the series is equal to the natural log of 3 minus the natural log of 2. And so I'll let you pause if you need to see that again, but I'm going to go ahead and get rid of that and change these to the same color. And so continuing this pattern, it appears like each term in the series is equal to the natural log of that term, natural log of 4, minus the natural log of the number prior to it. Now again, it looks like here the pattern doesn't hold, but it actually does. And I'm going to go ahead and write the first term as the natural log of 1 minus the natural log of 0. Now this creates a lot of problems because we know, hopefully, from the rules of properties and rules of logarithms that you are not allowed to take the log of 0. But for right now, let's just keep this in here to help us recognize the pattern. So the first term in the series is the natural log of 1 minus the natural log of 0. The second term is the natural log of 2 minus the natural log of 1. And again, don't simplify the natural log of 1. And then the third term is the natural log of 3 minus the natural log of 2, and so on and so on. So it seems like the pattern here is the natural log of whatever the term you're finding minus the term previous. So the nth term, by that rule, would be the natural log of n minus the natural log of the term before it, which is n minus 1. And so then using our properties of logarithms, we can rewrite this as the nth term. And when you subtract logarithms, subtraction condenses back to division. And so it's equal to the natural log of the quantity n over n minus 1. And so this is our answer for 3D. Now, the trick here was this was not an arithmetic series. This was not a geometric series. And so the only way we could really come up with this rule is we had to expand these particular values to see if we could look for a pattern in the terms. And so I was going to stop there, but I figured I would do one more example to show you how this works. Is let's say I give you a particular series. And so the series, and I won't give you any of the rules for it, but I will just tell you that the series is 1/2 plus 1/6 plus 1/12 plus 1/20 plus 1/30 plus ... And I ask you to take this series, this infinite series, and write it so that I could find the nth term. Now, looking at this, we run into a few problems that don't seem to make this easier for us to find. First, I look at the series that I know, and that is this an arithmetic series? So if I look at what do I add to each of these terms to get the next term. And unfortunately for us, and I'm not going to go through all the fraction work, the values that I add here, if I say 1/2 plus what, in this case, I am getting smaller, so I'm really subtracting. If I say, what am I subtracting to get from here to here? We could find a common denominator, do 3/6 and 1/6. And I say, it looks like I'm subtracting 2/6, so I'm subtracting 1/3. So that looks like what we're doing here. But then if I do 1/6 minus 1/3, because if this is arithmetic, you should have the same common difference each time. 1/6 minus 1/3 becomes 1/6 minus 2/6, which is definitely not 1/12. So by that idea, this is not an arithmetic series. Well, then we look at our other possibility, and it's geometric. And I say, well, 1/2 times what gives me 1/6? So it looks like I'm doing 1/2 times 1/3. Okay, so if we do that same idea, it then looks like here to go from 1/6 times 1/12, I'm multiplying by 1/2. Definitely not the same values. And then even here, what am I multiplying to get from 1/12 to 1/20th? Definitely not 1/3 and definitely not 1/2. So that eliminates a geometric series. So it seems like we're stuck. We don't really have a rule to do this. We don't have a way to find out what it is. But what I'm going to do is something similar to what I did with the natural log, was I took these and I expanded them, or I wrote them in a way that allowed me to see a pattern. And so this one, even though it may not be apparent what the pattern is, what would happen if I rewrote this series not as 1/2, but I wrote it as 1 times 2 plus, and then instead of writing 1/6, I write that as 2 times 3 plus, and instead of writing 12, I wrote it as 3/4, and continue the pattern, 4 times 5, and 5 times 6, and so on and so on. And now, hopefully you see the pattern that each particular term is just the product of two consecutive integers. And so if this is my first term, this is my second term, this is my third term, this is my fourth term, and this is my fifth term, it looks like if I ask you what the nth term in the series is, each term is 1 over, and then you're multiplying two numbers together. It looks like the first number is just whatever the n value is, which is 1. Here it's 2, here it's 3, so it's n. And then the other term is n plus 1. And so this is actually our rule for the nth term of this particular series. And you don't have to expand the denominator. And so the bigger picture here is some series are arithmetic, some are geometric, some are neither, and we have to come up with creative ways to rewrite them to get them to basically show us what the pattern is. And they're not always going to be this obvious, but sometimes you have to do a little work. So we'll readdress some of these patterns here as we get to the next section. So hopefully that was useful for solving your 3A homework.